Okay. Is it showing up? We could just put Dallas over at my PC.
Let me try this.
Bear with us 1 second, guys. We're sorry. First time we did this here, so a little bit of a technical difficulty. Can you guys hear me? Give me a shout out in chat if you can hear me. Okay, thank you. Loud and clear. All right, so they can hear me. Got a few spectators here. Rabble crowd, a rabble bunch. Rabble rousers. All right, I'm gonna hand the phone off to you.
All right.
I guess you have to keep it that way. Yeah, it doesn't seem like it likes the horizontal. So is Dallas a moderator now?
He can at least chat.
Okay. All right. We have that over there if we need to moderate, I guess.
Here, take this. I'll go fix the moderator.
Okay. One more second. My wife's gonna set up a moderator here. Did you make a comment, Dallas? Just say hello. I told him. What?
I'm under Cheryl's account.
Whatever. Just say hello, everyone. There you go. All right, you showed up blue, so you're probably fine, Cheryl. Dallas should be okay. All right.
All right.
Let's do this.
Let's do this then.
Okay, guys, thank you for coming today. We really appreciate the time that you took to be here. It's like the very first live stream event that we've done here, so a little bit of, working things out, getting the kinks worked out, but we really appreciate the support that you guys have shown in coming here tonight. So we have our team. I'm Chris from Harmony Turbines, obviously. I'm the founder and crazy one who started this whole mess, but I think it's been a really, really amazing adventure so far. So we have my wife behind the camera here, Cheryl, who was kind of second on board after we started and helping with everything from an administrative and all of the care and feeding standpoint. We also have Dallas. He's manning the comments right now. And we have Jeshwan. He is one of our new employees. We just hired Jeshwan and Vic as our electronics engineers. Vic is on vacation, unfortunately. We should have had a cardboard cutout of Vic. We have Jeremy. Jeremy is our machinist. And then we have Bob Hadfield, who has been a long-time member of our team, probably even before Cheryl started, in a sense, because going back to when we were just talking about forming this company and what we should be doing. Eric is a contractor working with us for our working on the charge controller, so in step with Jeshwan and Vic on that. And basically at this point, other than Vic, we have the whole team here, and then we have some outsiders. I don't know if you guys...
Someone said Vic is on vacation due to his shocking experience.
Yeah.
That's videos.
Yeah. So this mess that you see in front of you is our attempt at helping you understand the journey of where we got to. So when we began Harmony, it was trying to come up with a solution that would give customers and the rest of the world a solution for small wind power generation, something that's really lacking in the world. There's a couple units out there, vertical axis units and horizontal axis units that you could consider small scale, but most of them have been a pretty inadequate end result. Now, that remains to be seen how these other companies will do and what they're going to be able to produce in the end, but it's our opinion that those companies have not really hit the nail on the head when it comes to small wind power generation. And hitting the nail on the head is kind of important in this regard, because just like the cell phone, there were bag phones and suitcase phones in the beginning, but they weren't really doing what we needed at the time. They were cumbersome, they died quickly, they had poor range, poor capability. The first person who came up with putting it all in that one nice little package, you know, whether it was Motorola or whoever, the clamshell that you could close and put it in your pocket, they hit the nail on the head. And from that point on, the industry kind of went vertical. That is our hope with Harmony. That not that we're going to be the best one out there, but we're going to be the first one to say, this is how it can be. This is something that's putting us maybe orders of magnitude above what's out there already. That's our hope. So Harmony is the answer to our attempt at answering the problem of small wind power generation, getting something good, something reliable, something affordable, something that makes sense, it's convenient, it's easy to use. All of these things have been, you know, maybe one company will answer or check off one of those items, another company will check off another, but no one's bringing it together into a cohesive unit. Our opinion is that that has not been done yet, which is why we're working so hard with Harmony Turbines. And it is our hope that we're the first company that kind of brings all of those things together. So it brings us to the generator. Right now we have three major prongs or three major avenues that we're trying to tie up and finish with our development of Harmony. That is the generator itself. The second is the scoop geometries, or the way that the scoops are attacking and approaching the wind and how efficient they are. And then the third is our charge controller. Each of these three areas was lacking pretty severely. And so Jeremy and I have been working time, you know, day in, day out for the last 4 months on trying to come up with better scoop geometries. We've got some really amazing results that we have been finding back there. So the scoop geometries will wait a little bit until we have our generator and the charge controller kind of under our belt, so to speak, and develop to a point where we're happy with those. The charge controller, we've got version 1 of the charge controller that we had rolled out a month and a half ago, and it worked okay on our number 6 generator that we had up on the roof, which was an off-the-shelf generator, but as soon as we hooked it into our newest generator, we pretty much blew the charge controller. And then we blew it again and again. We've blown 3 of them. So we need to change things about our charge controller. It's a really good problem to have. You know, if you're gonna blow something up, do it in a way that is really, really helpful to moving the project forward. And that's what we've done. So we're redesigning the charge controller now based around new specs, new performance parameters that we're seeing with our generator. And this mess here is what we went through when we were originally looking at an off-the-shelf generator, because it makes sense to see if we can use an off-the-shelf generator to shortcut our pathway to development. We can just take our turbines, put them with an off-the-shelf generator, and out the door with a completed product. However, the reality of that situation proved to be far more challenging than we had originally thought. A lot of the generators may tick one of the checkboxes that we need. We needed really low RPM performance. If we don't have low RPM performance on those generators, then we have to gear it up somehow. We have to use either a toothed pulley, a chain, or some type of spur gears, you know, herringbone gears. There's all kinds of different ways you can do it, but they add extra friction, they add extra expense, and they're, in the end, more points of failure when you have a gearbox in between your turbine and your generator. So ultimately, we wanted to find a generator that we could do one-to-one, just couple it directly to the shaft and have it perform within the parameters that we wanted. So as we go through the generators here, we're gonna give you guys a chance to actually feel, touch, play. You know, you can have at it when we go through here, but we've numbered them in a progression of how we bought them. It was like, you know, this was the very first one that we got way back in the beginning, and believe it or not, it was so close to what we wanted that we thought, why look any further? The problem with this, you couldn't buy them anywhere else. They were available only in one place in a very limited supply, and we couldn't change anything about it. So it was, the only thing we could do with it is hook it up the way it was and try and morph our project around the generator, which seemed a little counterintuitive. As we moved on from this generator not being the solution, then we started getting into other ones that we purchased where they were, the specs that we were giving the people was, we want to have something that produces 500 watts of power in a 300 RPM range. And will even take up to 600 RPMs if that's the best you can do. So a lot of these were purchased on the understanding that they were supposed to produce in that range, but in the end, a lot of them, for one reason or another, just didn't perform like we needed, or required too much torque, or it just underperformed what the manufacturer was saying it was doing. I am in no way pointing to and saying any one of these in particular underperformed, because there are some out here that, as others watch this video, they'll be like, hey, that's our generator. What's he saying? It didn't perform right. It didn't meet all of the checkboxes that we needed. Okay, so we need low RPM, we need high amount of output from it from a wattage standpoint. We needed the torque to be low enough that our turbine could actually spin it. And all of these kind of in one cohesive package was very difficult to find. So, I don't know if anyone is feeling particularly, muscular today and wants to come over and give some of them a spin for us, but we'll show you how this works. Any volunteers? All right. Thank you, Bob.
Okay.
And if someone could get the signature for the newcomer we have in the back there. Hello. All right, so this was the very first generator that we had, and we have our two volunteers, Bob and Karen.
I was just watching.
Oh, okay. You guys can come closer. Go ahead. Come on, crowd around. Yeah, you can each stand in front of one if you want. You can pick your favorite generator. Make it fun. Okay? We can only connect one at a time to the test panel here. So pick your poison. Make sure you've got one that you've talked to, and you're on an understanding that it's going to perform well for you. Okay? All right. So Bob, if you want to try this one, right now we have everything turned off here. So you're going to see the raw voltage that the unit's making. You're not going to make any amperage in the beginning. So when you spin it and you kind of simulate a low wind startup speed, just go ahead and start turning that.
Clockwise and counterclockwise.
Doesn't matter. Yep. So that's a pretty high wind that you're doing there. Okay. Low wind would be, probably a pretty lazy wind. That would be maybe like a 5-6 mile an hour wind. We're making about 40 volts here. Okay. We're not showing any amps because we don't have any load on it. But when we put the load on, this one is going to basically represent a very low load, but we need a high amount of voltage for it. We need to get up to 100 volts for that to come on. So I'm going to throw that on. You shouldn't feel any change, but try and get up to 100 volts with it, Bob. That'll, as soon as you bring this up to 100 volts, there we go. We're finally getting that to try and come on. Okay, don't wear yourself out. Now we're going to make it hard. Now we're going to show amperage. Okay, now we're getting up to about a half an amp there, and we're hovering in between 40-45 volts that Bob's making. Okay, so this is basically helping to understand where we need to be high on the voltage and at the same time allow amperage to flow. That's why this one, it was kind of performing well enough that we're like, wow, we've got it. However, when we started getting into the higher end, this thing would do some kind of weird locking up where it would actually like lock up so tightly because of the flux. I'm not sure if it was back EMF or what it was, but you'd get it up to we would do a 2-to-1 or a 3-to-1 ratio on our turbine, and as it was spinning faster and faster, it would just want to like lock up. So we went from this one over to a very expensive generator that we purchased there. Now we're gonna, we'll do no load, so go ahead and spin it.
Does it need to be plugged?
Oh yeah, I'm sorry. It helps if we plug it in, right? Okay, so go ahead and spin it like a low wind speed. All right, there you go. You're getting a whopping 10 volts. And that is a low wind speed. So right away, that one, we would have had to gear it up. So now let's go ahead and spin it faster. Now you're in a pretty good wind there. That might be a 10 mile an hour wind. We're up maybe around 60 volts. I doubt you'll be able to go fast enough to get that to even light up. Okay, so we can't even get that to light up at 100 volts. Now we're gonna make it hard for you, so be ready. Okay, it does make decent amperage. We're making about a half an amp at 40 volts there. So that's like 20 watts that you're doing. It's, very, very low. So that one, although it had high-end amperage that we could kind of employ, it was much too fast that we needed to spin it to really get the performance that we needed. So let's plug into number 3 there. And Eric is kindly volunteering for number 3, I see. All right, so this generator, without any load, low wind speed, we're only around 10, 15 volts there. And if we flick this guy on, can you even get it to the point where we can make 100 volts? No way. You know, in a super high wind, perhaps. Now let's turn on your amperage. You're making a quarter of an amp there, and you're going at a pretty good clip. So once again, this was going to require gearing up. It was nowhere near what we needed from a production standpoint. All right, number 4, we're not even gonna hook this up because this is an absolute lie. The Chinese company was like, oh yeah, this will make 600 watts or 500 watts at 600 RPM, no problem. Well, we spun this thing with a drill up to like 3,000 RPM, and you were only maybe getting 80 watts off of it. So it was a total lie. We don't even, you know, we could hook it up, but no one can spin this fast enough. We'd have to bring the drill over. It's ridiculous. So I'm not gonna waste time on this one. And we bought 2 Chinese generators like this, and they were just a complete lie. So I'm allowed to say that because we're not dissing anyone. We're just dissing the whole Chinese generator. Yeah, that was a mess. All right, so the 5th one that we went to, that was a very expensive generator. That one came from India. Again, if you spin it real slow, nice and slow, like a low wind speed, we're getting some decent voltage. So we're seeing 40 volts in that low wind speed. If we turn this on, can you make enough to bring this light bulb? There we go. So we can actually get up to 100 volts with that in a decent wind speed. That might be, you know, 12, 13 mile an hour wind. So we can get up in the voltage. Now, here's the amperage. It's a pretty difficult thing to sit there and get them both going. So you have about a half an amp at 60 volts. The trick is, can you do both? And that's like where it's really kind of difficult, the best of both worlds, where we're getting the amperage and we're getting the voltage we need. And you can see this is very dim, that's barely lighting up. So, you know, we could kill our poor volunteer here, but we're not gonna do that. So that was our 5th. The 6th one over here is actually a e-bike hub that we used in reverse. So it's an e-bike 3-phase, what they call a brushless DC pulse motor that they have on the back of e-bikes. So it's an e-bike hub. This one we had to gear up severely. So,
We have volunteer.
oh, okay. New volunteer. Your name?
Bill Bernard, Penn State Harrisburg.
Oh, okay. Hi, Bill. Now I recognize you. Okay, so you're probably not going to be able to do much with this because it needed to be geared up severely, but go ahead and spin it. Low RPMs in a lazy wind, we're only seeing about 5 volts. So we had to gear this up. We geared it up 3.29 or...
Yeah, we also did 4.23 and 6.27.
Yeah, we tried like all the way up to 6, a 6-to-1. That means every one rotation here was making 6, or one rotation at the turbine was making 6 at the generator. This one, it's going to be disappointing because you're not going to be able to do anything. I'm actually going to throw them both on, and you're going to see that you can barely get, I don't even know if you could get that to light up, even going like a maniac. So the only way this was going to work was gearing it up, which is consequently what we have had on the roof for the past 3 months. Longer, 6 months. Okay. This is the unit, or one of the units, that's on the roof. But gearing it up was the only way to make this work, and we were running into a lot of top-end issues with the torque requirements because of that gearing up. All right, so who wants to volunteer for, oh, we're not even going to cover that one. That one is the one we don't even have hooked up, because that was just on a whim. We bought it. It's a DC generator. We don't even have wires hooked up to it. That thing needed like 4,000 RPM. We tried it in the truck for a while. We got maybe 80 watts out of it. It's running down the road like 50 miles an hour. It was insane. So we finally, after all of this messing around and said, all right, we've got to go back to grassroots. We've got to go back to the initial problem and say, how do we develop from the ground up a generator that's going to suit our needs? So we already have a patented axial flux generator with a variable air gap. That means the coils are in an array that go around like the numbers on a clock dial. Okay, so they're facing upright and you have magnets that pass below them and above them at the same time. So there's platters that run above and below the coils. That's what's happening in here. A magnetic platter above, a magnetic platter below, and the coils in the middle are arranged around like, you know, the numbers on a clock. And then the magnets pass by them. Our patented generator actually has a variable air gap mechanism that we can control the air gap. And we initially thought that was going to be the way to go because you could start out with the platters far away, and then as you got your RPMs up, you could bring them down into close proximity. Turns out we didn't need to be that complicated in the small units. In much, much bigger units, maybe 100 kilowatts or something like that, 50 kilowatts and above, it would make sense to have a generator with that capability because it's never been done before. We hold the patent on it. That capability does not exist in the marketplace. So that variable air gap is what we have patented for our axial flux generator. And that's what makes a really, really exciting product for larger scale units. However, we're trying to launch with a turbine that we can produce that we don't need cranes and, waterfront, lifts and everything to make these big, huge turbines. It doesn't make sense. It doesn't scale from an economic standpoint to have a generator that's very complicated with all these mechanisms that really aren't needed in a small scale turbine. So the answer to that was what we lovingly call our SAF generator, Simplified Axial Flux, SAF. Simplified Axial Flux means in this generator, we just have a static air gap and we configured it to operate within the parameters we need. Low RPM startup, high amount of amperage that we can get from the higher RPMs, and extremely good voltage. This generator was the first one we made. We took a stab at, how many coils to use, what size wire, how many turns, all of these things that we had to kind of, take a shot at. We hit it very, very close to what we were aiming for on the first one. We would have stopped there and regrouped and then tested and made new permutations, 3, 4, 5 different permutations to test different things with number of turns, number of windings, size of the coils, the MGOE ratings of our magnets. These are only N42. We could, N35 magnets. In here we could go up to N42. We could even go up to N52 magnets. We could go to larger size magnets. We could go to a thicker magnet, a larger diameter magnet. There's so many permutations that we can change. We hit very close to what we were after. So what I don't want to have you thinking when you walk away is this is the end product that we're going to start putting on our turbines. This is just the beginning, just the very first unit that we made, and it was so successful that we said, all right, we should probably do a live event. We should probably do a reveal, probably show everyone what we have done and how close we have gotten with the very first swack that we took at it. So we went and we built 3 more. So we have 4 total to show you today. This one was a very, first configuration. It will be changed going forward to dial in exactly what we want. But for the purposes of our demonstration, you're going to see what we're talking about as far as performance goes. So who wants to volunteer? And okay.
All right, because this is the biggest size wheel. I thought maybe it might be.
Yeah. All right. So without any load, just very slowly, we're up to 40 volts there, just in a lazy wind. Now let's see if you can get it up to 100 volts. How easy that is.
Yes, no resistance around.
Okay. So you're able to get that up to 100 volts pretty easily. Now we're going to make it a little more challenging for you. You're going to, it'll be a little bit harder, okay? But your amperage that you're able to make is immediately at a half an amp and you're up around 80 volts. You're even bouncing up to 100 volts. Now if you put both hands on it, let's see if you can actually get them both to light up. This is what we're going for, guys. High amperage, high voltage, all in a package that we can do at low RPMs from the get-go without any gearing right off the bat. We have not perfected this yet, okay? So I'm saying that 4 and 5 times here today. This is just the first one, guys, the very first one. So the configuration that's in this one is also in the other ones, but we have made improvements with the design to remove some of the extra eddy currents that we were getting by shelling out a little bit more of the aluminum material on the inside to remove them from the magnets, so we remove the drag. We can make improvements to the outside for cooling purposes. We can now go thicker on our coils if we want to. We could put more turns on. We could go to different gauge wire. There's all kinds of things we can do here. The sky's the limit. We can change this however we want, but to hit this close to what we're shooting for with our very first one, it was phenomenal. It was like hitting a home run. So this unit was able to do in the first attempt what none of these other ones could really do for us. Not without a lot of messing around or gearing up or all kinds of goofy things. This unit allows us to be one-to-one directly coupled with our turbine, and that's what we're after. So we will adjust the coils, we'll adjust the magnets as needed as we go forward over the next couple months to perfect, I shouldn't say perfect, but to tune our generator to be exactly what we want for the end result. All right, so you guys, after we're done the live stream, you can play with this. We'll let you guys play with it as much as you want. One of the cool things that we do is just to show you, we have the ability to even, run a normal AC power tool with it. The other ones, this one was able to do it, but you saw quite frankly how it was operating very difficult at the low end. It's some of them, like we said, they can make amps, but they can't make the volts, or they need to be geared up. There were just problems all over the place with trying to bring the whole package together. A wind turbine is a challenging thing to power or to draw power from, because you start out with no torque. There is no other application that I know of where you start with no torque. Everything else, whether it's a hydroelectric dam, a nuclear power plant, a coal-fired steam power generation, or cogen with natural gas, they all start with a huge amount of torque, a huge amount of inrush power that you don't have to worry about your low-speed startup. Wind is different. Wind, you need to start with no torque at all. If your wind turbine doesn't start moving, you'd have to be up at like 50 miles an hour before it would overcome that torque, and you'd probably rip the turbine apart going from 0 to suddenly 50 miles an hour. So wind needs to actually start very slowly and get moving, get all that inertia going, get the centrifugal forces into effect there so that you can have the flywheel effect helping you. The big turbines out on the coast, a lot of people don't know this, but they need kicker motors to get them going. Back in the 60s, those kicker motors were actually 50 horsepower Kubota diesel engines that they had up in the nacelle, 300 feet in the air, and people would be like, why does that wind turbine sound like a tractor? Well, it's because the tractor motor just started up to get the wind turbine going so that after it gets it up to speed, it can shut off and let the wind take over. That's crazy to me. Nowadays, they use the electric motors that are already up in the nacelle to either have a kicker motor up there or just run the generator in reverse to get it going and get it up to speed. With our axial flux generator with the variable air gap, we would be able to sell that unit, not this simplified one, but we would be able to sell the patented unit to companies, and they'd be able to retrofit them onto wind turbines, existing wind turbines, just the way they are, without any kicker motor or anything, because they could start with the platters far apart, very, very little startup, little to no resistance for startup, and then as it gets going, the platters would move closer to the coils, and now you're generating your maximum power. So that capability with our patented axial flux generator is really, really cool. It's not worth doing at this low level, 500, 1,000 watts. It's not worth doing. The bang for the buck isn't there. It's just going to be too complicated or too expensive to build a generator that you would couple with a garage size or a backyard size turbine. It doesn't make sense. So that's why we have our simplified axial flux generator that we're revealing today. Does that make sense? Okay. Before we take a little tour to show you, I'll ask if we have any questions here from the crowd. Do we want to turn that on if there's any questions?
We also have some internet ones.
Okay. We are going to show the performance at 2 other stations here. So how are we on time?
We're a half hour in.
Okay, so we're fine. Did it come on?
What do you envision as the method by which you would adjust the plates on your variable air gap? Is this like a control loop?
Again, that's not this simplified one. We've already worked that out. We already have that mechanism in the 3rd iteration. So that development was kind of going on in secret behind the scenes. We built a Mark 1, then we built a Mark 2, and we're on the Mark 3 and 4 now with that, the capability to do that. Because you ask a very valid question. It's an incredibly challenging feat to overcome. You've got to hold those platters radially in sync with each other. You have to hold them planar to each other, and you have to allow them to slide up and down. I had 2 different times I challenged engineering students at university level to come up with a mechanism to do that. No one could even come close. Doing all 3 of those things efficiently and easily, cleanly, is incredibly hard to do. We have done it, okay? So we've already got, you know, the units in the back, that Mark 1 and Mark 2 and the Mark 3 that we were working on, we put on hold because we're a small startup. We only have so much money. It's like, what do we do? Do we keep going with this patentable technology and try and roll this out, or do we go down the line of finishing our turbines and start selling this and then go back to developing that? So you kind of have to juggle a little bit and say what's going to get us to the finish line quicker. And right now, we already know we've got most of the things worked out with the furling mechanism that's like running beautifully. If we can lock down the generator and the charge controller, all we have to do then is put it together and we can go to market with that. And so that's where we were at. We'll come back to in another year or 2, or we'll partner with another larger group to do the final development on our patented axial flux generator. So that mechanism is, it's not, it's controlled with servo motors, I'll say that. You know, so it is an electronic means that they're controlled, and it allows us to dial in the power profiles then for specific RPM ranges. We can, you know, come to whatever air gap that we want to. So it'll allow us to control that. It's not just an analog like counterweight system or something like that, or a ball governor type of thing. Any other questions? Do you want to give, oh, you have the, okay. Yeah, just use Jeremy's, Dallas.
All right, first from Rick Z. He's asking, do we have a power curve for the generator?
Say it again.
Do we have a power curve for the generator?
Yes, we just mapped that yesterday. But again, I will remind everyone that this is the first version. So that power curve that we have for this first version is going to change drastically as we change all the different variables that we can in here. We're not going to publish, well, maybe we will publish that. There's really no harm in publishing it. We can show the power curve of what this initial generator did. We ran it up to 400 RPM yesterday and we did the testing on it. So we can share that. That's fine. We'll just caveat that to say it's the first version, you know, our first SWAC. And what did we get up to, Jeshwan? 600 watts at 400 RPM with it, yeah. So, any other questions?
Yes, another question from William Korb. Using your CNC machine, are the aluminum parts easily reproducible, or is this a one-off?
No, they're incredibly easy to reproduce. We banged 4 of them out in a week. Yeah. And we did that so that we had some stuff to show you guys. We didn't just want one generator here that's locked down and clamped to a table and we have to, you know, do a bunch of things to get it off. We've actually got one on the turbine behind you and another one on the turbine at the front. You walked right by it. So 2 of our generators are actually mounted to our turbines right there.
Another question from Tear It Up Sports. How soon is this being attached to the roof unit?
We're probably going to do a couple weeks of tweaking to dial in the performance of the generator, mainly changing the core, the coils, changing some parameters there with the coils. But our hope is really to get it up on the roof as quickly as we can. These are sealed bearings, so they should be waterproof, but we have the keyway to worry about. So Jeremy and I were discussing ways that we're going to pretty much waterproof this one access where water could get in, but once we come up with the way we want to do that, we could put it on the roof, because the entire unit, other than that, is perfectly sealed. So it's actually going to lend itself pretty well to being out in the environment.
Another question is from Phil B. What's the realistic timeline for beta units in the field?
As soon as possible. I mean, we have been saying all along, as soon as we're happy with the performance of the alpha unit, then we're going to start rolling out our beta program. But remember, we've got our generator we want to dial in, then the charge controller. Now those two, obviously you're seeing how close we are already with the generator. And while we're working on this, the guys are going to be working on the charge controller simultaneously. We've got 3 team members pretty much able to throw a lot of brain power at the charge controller. We've had version 1 of the charge controller. You're already working on version 2 of the charge controller. So we don't have a ton of work to do there. We have some tweaking to do. So really, the tweaking on the generator and the charge controller are going to go hand in hand. We will put those units up on the roof with the scoops that are already up there. But we have released in other videos that those scoops that are on the roof, the unit behind me, if you swing around here, that unit, if we say that performed at a level 1 on an arbitrary scale, it was performing with a power output of 1. The unit that is behind over there with the single scoops actually doubled performance. So we got a 2 on the same scale. So we doubled our performance. That one on the far end is also what's up on the roof. But in our wind tunnel testing, guys, we have actually been able to achieve numbers that are so good we're almost scared to say it, but we've seen numbers as high as 10 to 12 on that same scale. So it's such a huge leap that that's what we did other videos explaining what other testing we're doing with the outdoor air testing, the open air testing, to make sure that we're not seeing false positive results with the wind tunnel and assuming that we have like this really amazing end result. We're going to make a choice of the scoop geometry that we like. We're going to build it full size and we're going to put it up on the roof. And then if we're happy with the performance, then we'll take it and we'll add our furling mechanism to that scoop geometry. So the first one that goes on the roof with the new scoop geometry is not going to furl. We'll add the furling technology to that after we see that the performance is matching what we were getting at small scale. So there's a couple steps that we have to do before we go into the beta program, but we're rapidly approaching that point where we can get into beta. It's kind of like, the light at the end of the tunnel, it's there and we can see it. This was a huge step towards that. Any other questions?
Yes.
They keep rolling in.
Okay.
Yeah, as we're going, they keep rolling in. From Ghostlight, we have what kind of wind speed is needed to start the simplified generator?
Let's go show you that. So demonstration number 2. Is down here. Now, the light coming in is a little bit hard. I'm actually going to close this so that it helps. Nah, it's okay. So this is our generator hooked up to a very, very low load because all we're demonstrating here is low wind speed startup, okay? This is just a couple watts. That's all that this little light array is going to draw. So it is direct coupled from our generator directly into the plug for the little LED lights. And this answers the question directly that Dallas just asked, or the online person just asked, of how slow the low wind speed startup is. There it is, guys. So if anyone wants to come in and give it a push. Young man, come on. Give it a little push there.
Cheryl, let's come a little closer so we can see the lights. Okay.
So you can see even in the slightest breeze. And remember, these are not optimized scoops. These only performed a 2 We've got ones in the back that are performing 10, 12, even 13, I think, in one case. Jeremy's giving me the nod. We're a little bit scared to say that we've got ones that can perform a 13 on the scale that this only performed a 2, but the unit on the roof does very, very well, even with the 6-to-1 gear ratio that we had. So we've seen very good results. We know that the unit up on the roof is able to put out the torque. You can see just by me doing this that we're getting the power even at that low wind speed.
That little turn.
I'm sorry?
What would you approximate the wind speed to be with that little turn?
Probably like a 3-mile-an-hour wind. I don't know. And again, this is only like up on the roof, the 3 and 4 mile an hour winds will lazily turn our turbine around this speed. With the better scoop geometries, we might even be down in the 1 to 2 mile an hour range where we start getting rotation. So that would be unheard of, you know, if I don't know of any reliable wind turbine out there that can produce. Now, it's not magic, guys. You're not going to make 50 watts of power at 1 mile an hour wind. You're only going to make 1 and 2 watts of power. But we have to bring it down to the areas where it makes sense. People in rural developments with houses, with small businesses, they're not going to have 60 mile an hour winds like you have 300 feet in the air. They've got low winds, so we're trying to build units that capitalize on that help to produce in the range of wind that the average customer will have. Sure, our coastal customers, our boating and RV customers, they're going to have awesome wind because they're out on the coast or whatever, and those units will partner with companies. We've already got dozens of companies contacting us, asking us to partner with us and work with us to take our design and mass produce it for boating and RV, yachts, catamarans. We had Carnival Cruise Lines contact us. We've had Lawrence Livermore National Laboratories has reached out to us. What we have here is something very exciting if we can just finish the few final things that we have. And right here, you're seeing, guys, you know, you're seeing the fact that this generator, and that's not geared up. That is a 1-to-1 coupling right there. One rotation on the turbine is 1 rotation on the shaft. That's it. And we're getting power output. So that is our actual, you know, first version, if we want to call it Mark 1, Simplified Axial Flux, SAF Generator. The other one we have over here, it's really not hooked up to anything because there was only so much time we had before we did the live stream. So this is another one hooked up here to our original array, and you know, we just really hooked it up to show you how easily they can be integrated onto our turbines. So they're demonstrating how quickly we can lock them in, put them in play, and in the event where we need to replace one or something, we can just drop it off, put a new one on, and you're ready to go again. Let's go back here to the back end, and we'll close out our live stream with this demonstration, unless there were more questions we needed to address.
There were a few that came in.
A few? All right, how about we hold them till after this demonstration?
All right.
Okay, some live ones. You might have to squeeze in a little bit. So what we have here is a milling machine, and we're just using it to turn the shaft on the generator. We have this set so that it'll spin at 300 RPM. We're not yet sure what our scoops are going to be spinning at in the final configuration because Jeremy and I are still working on different scoop geometries. But 300 RPM at the high end at a 25 mile an hour wind is not out of the question. We'll see where we end up. The beauty of it is we can tweak the generator to whatever we need to from an RPM standpoint. You guys have seen the results of how configurable they are, what we can do to change them and make them operate how we want. So we have the oscilloscope here that's going to show you the wave function. In fact, if I take it out of gear, it's okay.
Got it?
Yeah, you can hold it. It's hooked up to the, it's too difficult to turn right now because I have it hooked up to the load and everything. Let's see. Nope. Okay, didn't think that one through. I was gonna show you the waves. We can hook it up on the unit out there and let you see the waves that they make. So just hold it up though, because we're about to show this. When we turn this on, we're going to be running at 60 hertz, which is the same power that you get at your wall outlet, 60 hertz. And we're lighting up all 120 watt bulbs here to full brightness. 120, so that is 480 watts coming off of this right now. And you're welcome to come over and feel it. Right here, we're showing 60 hertz, and we're showing 113 volts. So this unit is basically producing the same exact single phase current that you're getting at a wall outlet right here, right now at 300 RPM. That doesn't mean to say we're gonna be feeding 110 volts into your house. This is gonna need to go into a battery bank or something. But that's what you're looking at right there. So you're 112 volts, 60 hertz, 480 watts. So we already know right off the bat that with this very first Mark I simplified axial flux generator, we've come incredibly close to our target. We'll do a little bit of tweaking as we continue testing and we put it up on the roof. We'll kind of, I guess, we'll make adjustments as we see that we need them, whether we need a little bit more voltage or we need less torque or more torque. You know, there's a lot of things we can do here, especially with changing the coils, changing the magnets, or even changing the configuration of the units themselves. Unfortunately, I'm not gonna crack it open and show you the internal workings of it because we have to keep some things secret. We will show you, as we've promised, everything that we can show you. And right now, showing you the performance of it is pretty much what we've been wanting to do. Suffice it to say, producing these is a very simple process. Like I said, we made 4 of them in a time crunch in 1 week. So I'm really pleased with it. I hope you guys see the actual benefits of what we've done here, the implications of what we have done here. We'll take the oscilloscope over. Jeshwan, if you want to disconnect this and we'll bring it over so that people can see the waveforms and stuff then at the bench. That would be cool. Okay, we can open it up to questions now online, Dallas, and we'll go back to where the fans are so it's a little cooler. How are we doing on time? Okay.
Maybe check here to see if there's a question.
Yeah, any questions here from the crowd after you guys have seen? Go ahead. What's your name?
Anthony.
Anthony, okay.
Why is it that the material for the scoop is made out of metal instead of something else?
When you're prototyping, you need to work with things that you can easily and quickly produce, change, alter, configure without getting into a whole supply chain of, so if you wanted to do fiberglass or if you wanted to do carbon fiber reinforced things, scoops, you would need to go spend $400,000 having incredibly expensive molds engineered and manufactured, and then you'd have to have those poured and set, and then you go to test it and you're like, oh crap, we need to cut 2 inches off this, or we need to change this. Now you've got to go back and spend another $400,000 to get that new mold done, go through the process of getting it all. So you work with materials that you can very quickly and rapidly prototype, test, change, and iterate. We have the ability to machine and work with the metal in our shop here. That's why we picked aluminum, because we can make all of the components literally sometimes within hours of what we need, instead of weeks sending them out to a company or months to another company to do. Make sense?
Yes.
Good question.
Can you 3D print those big scoops?
We have a set of 3D printed ones somewhere. I don't know where they're hiding.
The white ones in there?
I was just wondering about 3D printing.
Is it the white ones in there?
No,
Variations.
there's one set.
Take for the variations of this.
We had one set of units. They were probably 2 feet in diameter, I think, and they were incredibly expensive. They took weeks and weeks to come from China. Nobody had printers 4 years ago the size that we needed to print something like that. Maybe now, 4 or 5 years later, there are some of them. Yeah, they're back on the back shelf. They're hiding. We can show them to you later. But yeah, we thought that too. We went the route of 3D printing the stuff right away. But believe it or not, it was far more difficult to do that than, you know, getting some used machine equipment, machining our own. because you can do rolling, you can do welding, you can do crimping, you can do forming on aluminum, and of course you can machine it, where 3D printing, everything you do, you have to, if you don't have the size printer you need to do it, you're kind of screwed. You've got to rely on other people to do that for you. Good question, though. Thank you. Any other questions from the group? No? Okay, questions from the online crowd?
All right, resuming where we left off, we have Christian Zoll. Many generators are based on 3 phases, which is not required to load batteries.
Correct.
How about your version?
I already said it. It's single phase.
Okay.
Yep. And we can do what we want here. So why would we sit there and try and force our product into the paradigm that exists out there in the market when we can simply do what we want? In the end, all we need is single phase to charge the batteries properly. And single phase allows us to do a lot more things with our voltage and our amperage that you can't do with 3 phase. So that is what we have here. It's a single phase generator. Good question.
All right, and then Phil B is asking, regarding the wind turbine, is there a wind speed to RPM chart?
That will come, it'll be different for every scoop geometry we have. So it's not like there's any one wind speed to RPM chart. As soon as you change, the wind speed to RPM chart is different for turbine array number 1 than it is for turbine array number 2, 3, 4. We have 130 or something like that little models that we have printed up in the back. And so all of those different wind turbine geometries have a different RPM to wind speed profile, every single one of them. And that's part of the work that Jeremy and I have been doing. So yes, we have those charts in miniature, and every single one of them is different. So we're not going to publish that because they'd be all over the place. That's part of the secret sauce of what we're finding. In fact, a lot of, Jeremy can even speak to this, a lot of what we had going on in the research that we were doing was that it appeared a lot of the research was either incomplete, or it was just hurried, or they maybe didn't take it to the, the 5th and 6th degree that they should have when they were doing their testing.
Right.
Yeah.
Yeah, we just did a lot of experimentation, and we were very diligent about controlling the different parameters, so that when we made changes to a turbine, we were changing one particular feature of the design.
Right.
Not having multiple changes. So therefore, we came up with some interesting results.
A good example Jeremy likes to talk about is they would do testing on a turbine that was this diameter and this height. And then they'd say, well, let's make it taller and see if that's better. Well, of course it's going to be better. You just increased your surface area. But to do that test properly, if you make it taller, that means you'd really have to shrink the diameter. Otherwise, you're invalidating your test. And a lot of the tests out there, when you really dig into how they did their testing, they didn't cover those things. It's like they weren't thinking about it from a first principles standpoint. They were just changing one parameter, but of course you're going to get better performance when you go higher and keep your diameter the same. To do it and keep it the same, you have to keep your swept area, your width times your height, the same. We have done that. Anything else you want to say? We dug through lots and lots and lots of data, and it was very disappointing. Even ones that are highly regarded tests that are out there, that have been out there for 20, 30 years, we were like, as we get under the covers and start looking at it, we're like, oh my God, they never even took this into account. They never took that into account. We're trying to do that. We're trying to be far better than those studies that were done. And a lot of times in their defense, they're under a time crunch. They've got to get their dissertation completed by a certain amount of time, or they don't pass, or they don't graduate, or they lose their funding, whatever. So they can only do so much with their testing. We're not under those same time constraints. I mean, we are if we run out of money, but we're hoping that we can be smart enough that we don't do that. We are looking at all those permutations. We're looking at all of those differences and nuances and taking them into account. So it's been a pretty wild ride with the wind tunnel testing, led to a second open air testing device, and even one that's spinning right now that we can take outside in the open air outdoors. On top of the ladder, you see those little guys spinning right now. That is the third iteration. They're all offshoots of our wind tunnel testing. None of the other companies or none of the other papers went to any of these lengths. We've even built our own eddy current brake in miniature, something that we searched high and low for anything that could give us the amount of consistent drag on the little mini turbines that we needed to see them. They didn't exist, so we built them. And that's just how we roll here. We see a problem, we overcome it. Everyone's like, oh, there's got to be a solution to that already out there in the market. There isn't. If these things were solved years ago, you'd already have a product that you could buy. You can't because the problems haven't been solved. We're the first, in our opinion, the first company sitting there trying to do that. So, it's that fight of how good is good enough before we go into production is really the final question.
The bell just rang, FYI.
Okay, so we're at an hour. I don't think anything happens. YouTube doesn't blow up, but
I just wanted you to know.
okay.
There's still more.
More questions? All right. Thank you, Jeremy.
Yeah.
Our next question from Emmanuel. Can you please give the weight of a complete turbine?
It will change as we, some of the new scoop geometries we're looking at, we may even be able to remove the frame from the unit. Sorry. Talk to the camera. We may talk to the people. We may be able to remove the frame from the units with the new scoop geometries because a lot of what we're seeing is shorter, fatter turbines are actually giving us a lot better performance. So the weight's going to change. Right now, the units as they stand, what are they, like 800 pounds? Something like that. Yeah, but it's probably going to be considerably lighter when we get to the final version. They're just heavy and overbuilt right now. You always overbuild your prototypes because you don't want a mechanical failure to be the thing that kills your experiment.
All right, and a follow-up question from Ghostlight with the regarding the speed of the wind needed to start.
Mm-hmm.
Why spend time developing the movable magnet platters?
Because for higher power applications, that could be a gold mine. If you can imagine a product that could be retrofit into every single industrial and commercial wind turbine out on the market where they wouldn't need to use kicker motors in those units, you've got something there that's a gold mine. At least in our opinion, it's a gold mine, and everyone we've talked to so far shakes their head and says yes. That's why we would go down that route. We're not spending time developing that right now because we're waiting until we're in production. Goodness. We're waiting until we're in production with our current units, our current residential size units, before we go down the development path. That could be another 2 years of development and a lot of money. So we're not putting time and effort into the development of that at this time, but we're keeping it on the back burner for later.
All right, and then we have one from Restless Falcon. Have you tested any of the new scoop geometries with benefits you were getting from multiple units near each other?
No, we haven't built any of the new scoop geometries full size yet. That's what we're waiting to do. So we will test with clustering effects later on. We have to be careful about that because there's another company out there that actually patented the clustering effect. So we're going to, have to dance around that carefully. We're not going to be setting units up in a clustering effect, but we'll let people know that they can do it. You okay?
I didn't think that was the question, but maybe I misunderstood the question. Okay. Were there any more?
Any more?
Yeah, one last question.
One
It's
last
a
question.
simple one. How do you convert single-phase DC to charge batteries?
It's just a full wave bridge rectifier. It's a simple 4 diode setup, and you have 4 diodes in a diamond pattern, and you get a full wave bridge rectifier. It's very simple to convert AC into DC.
That's it.
Okay.
Talk about our raise?
Yeah. Thank you for. So guys, we do have a raise going on right now. Many of you here already know that, but to our viewers online, we have a raise going on right now. If you like what we're doing, if you like the principles and the values that we at Harmony Turbines hold near and dear to our hearts, if you see the benefit in what we're doing, then please consider investing in our company. We could certainly use the investments. We are at this time raising depending on when you watch this video, we'll probably be open for a while longer. But we do have a raise open right now. So hop in, see if, just go to harmonyturbines.com. There should be a link right there that says invest now. If that link is not there, then you've missed the opportunity. So we're trying to do as little raising as possible. Our goal is to do minimum amount of raising to get across the finish line and be in production to be profitable. So, if you want to invest in Harmony, you might want to hop on it as quickly as possible. Any questions, you can always email or give us a phone call. We'll be happy to answer them. And we are here to help, every single one of these problems that we've been talking about as we've done our live stream today is what we're looking to solve. Giving decentralized power generation around the world could be huge, especially for developing countries. And access to clean, easily maintained and afforded electricity is something that many of these places are lacking. So you could get into water desalination, you could get into water that's being condensed out of the air in places, so you could turn, basically with power generation, you can also get into water availability in developing countries and things like that. If you decentralize power, you can escape all of having, the grid or the power lines going all over the world, running out all over the place. You can get rid of all of that. Decentralized power makes an infrastructure much more stable. You don't have one single point of failure for millions of customers. We're looking to help that revolution take place. Decentralizing power generation around the world is one of our main goals and one of our main tenets in why we formed Harmony. Making that affordable and available to the global community is, of course, the end goal there. So thank you. We're here because of you. We're here to help make the world a better place. That's our goal. We're not in this to become multi-billionaires ourselves. We're in it really to bring this technology to fruition, to bring it to the world, to make the world a better place. So that's what we're about. And that's why everything we do is trying to do that in the most common sense way possible. So from all of us here at Harmony Turbines, all of our guests today, we just want to say thank you for coming out and spending time with us. How many did we have on the live stream at the peak?
Peak, it was just over 100.
Over 100, nice. Okay, that's really good. Thank you. All right, guys, thank you for everything. And to our group online, we'll say have a good day and we'll catch you on the next update. Take care, guys.